Hi everyone. Today we are going to explore how Note app work, focusing on its core functionality, especially how sync work across multiple devices and how conflict are managed. For this video, we'll focus on offline mode and the sync manager. Note is digital note-taking app that allow you to create, organize and sync note across multiple devices. You can add text, image, list, and more, making it easy to capture ideas anytime, anywhere. To start, we will have basic functionality which help to save title and description only. As you can see, we have app running on two devices. Let's add some data on first device and then add different data on second device. Currently, the app is in offline mode, so all data is stored locally on each device. Now let's go online. The app starts syncing with cloud database. As you can see, the data is synced between both devices correctly. Next, while online, let's try adding more data on both devices. After a few seconds, the new data appear on both devices as you can see. Finally, let's try deleting some data while we online. As expected, the deletion is reflected on both devices properly. Now that we have seen the app in action and how sync work, let's take a closer look under the hood. In the next section, we'll explore a low-level diagram of the app to understand its core, architecture, how data flow, and how the sync manager handle conflicts. Let's look at class diagram. First, we have note listing. It displays a list of notes and allow user to delete or update them. From this screen, we can also navigate to create note screen, which is used to add or edit notes. All these actions use the note model for managing data. Next, the UI alone can't do anything on its own. It needs business logic to perform real action. That's why we have a separate business logic layer. We use create note view model to create, find and update notes, and another view model that we call list view model, which help to list and delete notes. So to keep our business logic organized, we got a few interface. Things like add note, get all note, get note by ID, delete note and update note. Now you might be thinking, why not just pull all of these into one class since they are all about notes? Well, good question. The reason is we are following this solid principle. If we throw everything into a single class, we end up breaking couple of things, mainly the list of substitution principle and the interface segregation principle. Basically, different part of our app only need specific interface. So if we mix them all together, some parts will go unused and that's not clean or maintainable code. Next, let's talk about the model. As you can see, we got field like ID, title and description, pretty self-explanatory. Then we have a create timestamp, which stores the time when the node is first created. Next, there is update timestamp, which change whenever we update the nodes. There is also a sync timestamp, used when node is actually synced with the database. The deleted flag helps us to mark a node as deleted instead of just removing it. And finally, the version field. That's update every time we make a change so we can track a different version of the node. Now the next class is our database manager, and this one play a key role in saving data. When a notes get created, it passed from business logic to database manager, which then handles saving it. It includes all the method we need: add, get, update, delete and find notes. Next we get a really important component in our entire ecosystem, the sync manager. The sync manager starts running as soon as the application launch. Its main job to find any outdated data in database and push it to cloud. It also poll for new data. So for example, if a user login from another device or someone else update the same note, the sync manager makes sure everything stay up to date. It comes with few handy utility methods like load out of sync data, perform sync and push data to cloud. It's pretty smart. Syncing happens in both directions, one after another. Before pushing data, it even logs the database to make sure no new data is added during the sync. And if something failed to sync, the sync manager automatically try again to resync that data. So how does sync manager actually know what data need to be synced? Well, it's used something called sync timestamp. Any data that's newer than this timestamp is considered outdated, and the sync manager will try to sync it with the server. When the app closes, the sync timestamp gets saved using another component called the preference manager. The preference manager basically stores value in secondary storage, so even after the app is closed, the last sync time is remembered. Now, to actually perform the sync manager needs to push and pull data from the cloud. That's where network client and network layer come into play. They handle all the communication with the cloud, sending new data and fetching updates. And that's how all these components, the sync manager, preference manager, and network layer work together seamlessly to keep everything in sync. Let's talk about some of the challenges we faced and how we solved them. So initially, we planned to have running queue that sync data to the cloud. New data would be added at one end and sync data would be pushed to the cloud from the other end. But here's the problem. If new data get added while syncing is still happening and the previous version of Note failed to sync, there is chance the newer version might sync before the older one. That can cause conflict. To fix this, we switched to using a set data structure. With a set, we don't need to search for data. It works using hash, and our model ID acts as a unique hash key. This way, we always update the correct node and syncing stays consistent. The next challenge we faced was during the sync process. At first, we were doing pull and push operations separately, which caused a lot of issue. For example, if data was being pushed to the cloud, while at the same time new data was being pulled and updated in database, it created duplicate and conflicts. To fix this, we changed the process to run in sequence. First push, then pull. This way, we all read and write operation happen one after another in order keeping the local database clean and consistent. The third challenge came from immediately pushing data to server, whatever a node was inserted or updated. This caused duplicate sync because every new node triggers this sync mechanism, sometimes override ongoing sync. To fix this, we added a lock on the upstream during sync. Now, if a sync is already in progress, new data wait, it's done, preventing conflict and keeping everything consistent. The fourth challenge was the creating node ID locally. At first, we just used simple increment, but this caused duplicate ID if another user creates a node at the same time. To fix this, we start combining the user ID with timestamp, which make the ID mostly unique. However, there is still a potential issue. If a user changes their system time, it could still create conflict. One way to solve this could be to use UUID or server-generated ID instead of relying on local timestamp. That way, each node ID is guaranteed to be unique, no matter what the system clock says. The fifth challenge happened during polling. Every time new data appear with a greater sync timestamp than the local data, we update the local node. But this caused a problem. If the local node was updated first, it could get overridden by the incoming data. To fix this, we start using version number. Now, if the upstream data has greater version, it is considered as a conflict. Right now, we are simply reject that update, but in upcoming video, we'll build a conflict resolution manager to handle this smartly. If you are interested in building a conflict resolution manager, drop a comment and share your approach. Now let's talk about what we are planning to build next. Conflict manager, so that if a conflict appears in any node, the user can resolve it easily. Real-time collaboration, allowing user to update node directly, just like Google Doc or Google Keep. User management, so user can log in securely with the username and password. Rich text component. Right now, we only save simple titles and description, but soon we want to support image, video, GIF and more. If you are interested in building this and learn along the way, drop a comment and share your ideas. Let's start with the Note View UI. First, we need a data stream to show notes on the screen. We take a list of notes, pass it to lazy list, and Compose take care of rendering each item for us. Next, the business logic. The UI talk to the view model. In the view model, we have two main functions: get all notes to fetch notes and delete note to remove one. Pretty simple. Now the creation note screen. At top, there is back button to return to the previous screen. Then we have text field for title and description. And finally, a save button. When save is pressed, we check if note ID is -1. If it is, that means we are creating a new note. If the ID exists, we update the existing one. The create view model also have method to add, update and fetch a single note. To store everything, we use a local database. This is done with SQLite using Room provided by the Android SDK. Now the most important part, the sync manager. When syncing starts, it runs in a loop. It performs push, then pull, one after another. During the push phase, it first checks if syncing is already in progress. If not, it looks for outdated data and send it to the server. If pushing fails, it retry with resync. Whenever new data is inserted or updated, it waits for current sync to finish. After push is complete, we move to pull phase. Here, the app fetches the latest note from server. If a note has been deleted remotely, we remove it locally as well. Then we save the latest timestamp for the next thing. All network communication, both getting and posting data, is handled by our network manager. That's all for this video. If you like, please comment and share. Till then, stay tuned.